right, welcome back to the deep dive.
Yeah.
Today, we're going to be tackling something
Ambitious.
truly ambitious.
Yeah.
You sent us this paper outlining a new theory of everything
Whoa.
called the time force hypothesis.
Okay, a theory of everything, huh?
Yeah,
That's a big claim.
it's a pretty big claim, right? That's what makes this deep dive so interesting.
I'm intrigued for sure.
We're going to explore this hypothesis today and see if it, lives up to that name.
Yeah.
So essentially, it tries to explain the entire universe,
Mm-hmm.
from the smallest particles to the biggest cosmic structures,
The whole shebang.
all with just one principle:
Oh, okay.
energy-seeking equilibrium.
Interesting.
So, think about it. Right now, we have all these different models
Right.
for particles, for gravity, for the expansion of the universe.
Yeah, it's a bit of a mess.
It's a bit of a physics puzzle
Yeah.
with pieces that don't really fit together.
That's a good way to put it.
And the time force hypothesis is suggesting that maybe we're just looking at the puzzle the wrong way. Maybe there's a simpler, a more elegant picture underneath it all.
I like it. I like it.
So, are you ready to dive into a universe where everything is connected
I am. Let's do it.
by this flow of energy?
Absolutely. And the key here to understanding the time force hypothesis is this concept of a scalar field.
Okay.
It permeates all of space and time. It's everywhere.
A scalar field.
Yep.
I'm already getting flashbacks to physics class.
Haha.
Can you break this down for us?
Sure.
What exactly is a scalar field?
Okay.
And why is it so important to this hypothesis?
So imagine like a temperature map
Okay.
where every point in a room has a specific temperature assigned to it.
Mm-hmm.
That's kind of like a scalar field.
Okay.
But instead of temperature, it's filled with energy.
Got it.
And this energy isn't just sitting still, it's constantly flowing, trying to, even itself out to reach equilibrium.
So, like, if you had a hot cup of coffee in a cold room,
Exactly.
the heat would spread out
Right.
until the coffee and the room reach the same temperature.
Exactly. And according to the time force hypothesis, all of the fundamental forces and particles that we observe, right, emerge from this energy flow, seeking this balance within this scalar field.
Okay, I think I'm
Yeah.
starting to see how this connects.
Right.
But how does this energy-seeking equilibrium actually create things like particles? An electron isn't just like a blob of energy, right?
You're right.
It has specific properties,
Yeah.
like mass, charge.
This is where things get interesting.
Okay.
The time force hypothesis says that these properties, like mass, arise from the way energy interacts.
Okay.
Within the scalar field, think of it like whirlpools forming in a river.
Whirlpools. Okay.
Yeah.
Now you've got my attention.
All right, so these whirlpools,
Yeah.
they're actually vortex structures within the scalar field.
Right.
And they represent particles.
Right.
The mass of a particle, like an electron, is a measure of how much it resists the flow of energy in this field. The more resistance, the more massive the particle.
So essentially, mass isn't an inherent property of a particle,
Right.
but a consequence of how it interacts with this energy field.
Exactly.
It's like the particle is trying to swim upstream
That's a great analogy.
against the current of energy.
Yeah, and it's not just mass. Other properties like charge and spin also arise from the specific shape and dynamics of these vortex structures.
So it's like the entire universe is this giant swirling
Yeah.
dance of energy.
Sure.
And everything we see, from tiny particles to massive stars,
Yep.
is just a manifestation of this dance.
That's the essence of it.
Wow.
And what's even more impressive is that the paper actually derives
Okay.
specific values like the mass of an electron and the gravitational constant directly from the equations, describing this energy flow.
Wait, hold on.
Yeah.
They're saying they can calculate the mass of an electron just by looking at the equation for this energy flow.
That's right. They're not just plugged in arbitrarily.
That's incredible. It's like they found a secret code
It is a very elegant and powerful idea.
that unlocks the fundamental properties of the universe.
And it goes even further than that. The time force hypothesis also tackles some of the biggest mysteries in cosmology,
Right.
like the expansion of the universe
Right.
and the nature of dark matter and dark energy.
Okay, now I'm really intrigued.
Good.
Let's talk about the expansion of the universe first.
Okay.
Currently, we explain that with this mysterious concept called dark energy, right? That's pushing everything apart.
Yeah.
How does the time force hypothesis handle that?
Well, It throws dark energy out the window.
Whoa, okay.
Instead, it says that the expansion of the universe is a natural consequence of the energy in the scalar field dissipating over time.
So instead of needing this mysterious force pushing everything apart, it's more like
It's like a balloon slowly deflating.
a balloon slowly deflating.
As the energy inside spreads out.
As the energy spreads out.
That's a great way to visualize it.
Yeah.
It's not an external force pushing things apart.
Right.
It's the energy within the system.
Okay.
Naturally evolving.
Got it.
And causing expansion.
So it's not just about explaining what we already know.
Nope.
It's also making predictions about how the universe behaves.
Exactly.
This is getting more and more exciting. But what about dark matter?
Yes.
You mentioned the time force hypothesis has a different take on that as well, right?
It does indeed.
Okay.
Right now, we think dark matter is some kind of invisible particle, right?
Right.
That we haven't detected yet because it only interacts with gravity.
Mm-hmm.
But the time force hypothesis suggests we might not need these extra particles at all.
Hold on. Are you saying dark matter might not even exist?
Well,
But we see its gravitational effects all over the universe.
right, but those effects could be explained
Okay.
by the energy gradients within the scalar field itself. Imagine those whirlpools we talked about earlier.
Okay.
Those vortex structures representing particles.
Yeah.
They create dips and peaks in the energy landscape
Right.
of the scalar field.
Okay.
So instead of invisible particles clumping together
Okay.
and causing extra gravity, it's the energy flow itself that's affecting gravity in a way that we perceive as dark matter.
So the time force hypothesis proposes that what we observe as dark matter is actually a consequence of how energy is distributed and flowing within the scalar field.
Precisely. And this leads to some testable predictions, like a different distribution of dark matter in galaxies
Okay.
than what's expected from current models.
So if we were to measure this different distribution,
Yes.
it'd be a big win for the time force hypothesis.
Absolutely.
This is incredible. We've gone from a basic explanation of the time force hypothesis to talking about rewriting our understanding of dark matter and the expansion of the universe.
I feel like we've just scratched the surface, though.
There's so much more.
What else does this hypothesis have to say about the universe?
Well, it doesn't stop at cosmology.
No.
It also delves into the realm of black holes
Okay.
and even offers a new perspective on quantum gravity, suggesting there's a limit to how much energy can be packed into a tiny space.
A limit to energy.
Yeah.
What happens when you hit that limit? Does the universe just say, nope, not happening?
That's a great question, and that's one that the time force hypothesis tries to answer.
Right.
It leads to some pretty mind-bending implications
Oh.
for what happens at the center of black holes.
Okay, I'm on the edge of my seat. We've got to dive deeper into this. But before we do, let's take a moment to let all of this sink in
Yeah, take a deep breath.
for our listener.
This is some radical stuff. This is some pretty radical stuff.
It definitely challenges a lot of our current assumptions about the universe.
Right.
But what's exciting is that it's not just philosophical speculation.
No.
The time force hypothesis makes testable predictions.
Right.
And that's what makes it so compelling.
You're absolutely right. It's not just a beautiful idea.
Yeah.
It's a potential roadmap to a deeper understanding of reality.
Exactly.
Okay, let's jump back in. What does the time force hypothesis have to say about black holes
Okay,
and
right.
this energy limit?
According to the time force hypothesis, those infinitely dense points at the center of black holes, called singularities, might not exist at all.
Wait, so instead of everything collapsing into an infinitely small point,
Right.
there's a point where the universe basically says enough is enough.
That's the idea.
What happens then? Does matter just bounce back or?
That's where things get really fascinating.
Okay.
The time force hypothesis suggests that at this limit, quantum effects become dominant.
Right.
And a whole new set of physics might come into play.
Okay, I'm officially mind blown. So, black holes aren't just these cosmic vacuum cleaners sucking everything in.
Right.
They might be gateways to understanding the most fundamental laws of the universe.
It's a possibility. And remember, all of this is connected back to that one underlying principle.
What's that?
Energy-seeking equilibrium.
Okay.
It's the driving force behind the expansion of the universe, the behavior of dark matter,
Right.
and even what happens inside black holes.
It's like finding a hidden code that unlocks the secrets of the universe. And the best part is, it's not just a theory. It's a theory that makes testable predictions.
Exactly.
So we might actually be able to prove or disprove it in our lifetime. This is why I love science. But We're just getting started.
Oh, yeah, we're just getting warmed up.
There's so much more to explore in this paper.
Buckle up.
We'll be right back after a short break to delve deeper into the time force hypothesis. Stay tuned.
See you soon.
Welcome back to the deep dive. We're unraveling the mysteries of the time force hypothesis.
Still going strong.
A potential theory of everything.
Yeah.
That could revolutionize our understanding of the universe.
It's pretty wild stuff.
So before the break, we were talking about how this hypothesis explains things like the expansion of the universe.
Right.
And dark matter through this lens of energy-seeking equilibrium.
That's right.
And we even touched on this idea that black holes might not have these infinitely dense points at their centers that we call singularities.
It's a crazy thought.
Instead, there might be a sort of quantum firewall that prevents matter from collapsing completely.
Right.
But this hypothesis goes even deeper, right?
Oh, yeah, much deeper.
It delves into the very fabric of reality, touching on things like the nature of space and time.
It's a big one.
I'm dying to know more. What else does this paper have in store for us?
You're right. We've only just begun to explore the implications of the time force hypothesis. And one of the areas where it gets really interesting is in its approach to quantum gravity.
Okay, quantum gravity.
Yeah.
That's the quest to unify Einstein's theory of gravity, which describes the universe on a large scale with quantum mechanics, which governs the world of tiny particles.
Right, two of the biggest ideas in physics.
It's like trying to fit two giant puzzle pieces together that don't quite match.
That's a good analogy.
So how does the time force hypothesis help us solve this puzzle?
Well, it proposes this radical idea that gravity itself is not a fundamental force, but an emergent property of the energy flow within the scalar field.
So instead of thinking about gravity as a warping of space-time, like Einstein proposed, the time force hypothesis suggests it's more about energy seeking its lowest potential, like water flowing downhill.
Precisely. And this leads to some fascinating implications for understanding extreme gravitational environments like black holes. Remember that quantum firewall we discussed?
Yeah.
That implies a fundamentally different picture of what happens at the singularity of a black hole.
Right. The idea that there's a limit to how much matter and energy can be squeezed into a tiny space.
Yeah.
But if gravity is just an emergent property of energy flow, what does that mean for the incredibly strong gravity of a black hole?
It suggests that the extreme gravity near a black hole is a result of an incredibly steep energy gradient in the scalar field. Think of it like a waterfall where the water's rushing down with tremendous force. That's analogous to how energy flows towards the center of a black hole.
So it's not the mass of the black hole itself that's creating the gravity. It's the way the energy is flowing.
It's the energy flowing.
Or a scalar field. That's a pretty mind-bending concept.
It is, and it has the potential to resolve some of the paradoxes that arise. When we try to combine general relativity with quantum mechanics.
Like what?
For example, one of the big problems in physics is that our current theories predict that black holes should destroy information, which violates some fundamental principles of quantum mechanics.
The idea that information can never be truly lost.
Exactly. It just gets transformed.
So how does the time force hypothesis address this information paradox?
By suggesting that the information isn't actually destroyed within the black hole. Instead, it's encoded in the structure of the energy flow near the event horizon.
The event horizon.
Yeah, the point of no return for anything falling into a black hole.
So the information is sort of smeared out.
You could say that.
On the surface of the black hole, like a cosmic hard drive.
That's a great analogy. It's a radical departure from our classical understanding of black holes. But it offers a potential solution to this thorny problem in physics.
This is incredible. We've gone from talking about energy flowing like a river to the possibility of black holes storing information like giant hard drives. It's amazing how this one hypothesis can tie together so many seemingly disparate concepts.
It's a powerful idea.
It is, and it doesn't stop there. The time force hypothesis also has profound implications for our understanding of space and time themselves.
Oh, absolutely.
In Einstein's theory of relativity, space-time is a smooth, continuous fabric that can be warped by gravity.
Like a rubber sheet,
Like a rubber sheet that gets stretched and distorted by massive objects.
Exactly.
The time force hypothesis suggests a different picture, right?
It does.
What is it?
It suggests that at the most fundamental level, space-time might not be
Yeah.
smooth and continuous after all.
Okay.
Instead, it might be a turbulent sea of quantum fluctuations.
Quantum fluctuations.
Yeah, something physicists call quantum foam.
Wait, hold on. Are we saying that space and time are not continuous,
Right.
but are actually made up of tiny, discrete units? Does that mean we're living in some kind of cosmic pixelated reality?
It's certainly a mind-bending concept.
Yeah.
And the time force hypothesis suggests that these quantum foam fluctuations could have measurable effects on particles traveling vast distances.
So, like, imagine a photon traversing billions of light years.
Right. According to the hypothesis, it would experience slight delays due to these space-time fluctuations.
So we could actually measure these tiny delays.
Potentially, yes.
And use them to probe the structure of space-time at the Planck scale. That's like looking at the universe through a quantum microscope.
It's a remarkable possibility.
Wow.
And what's even more exciting is that experiments like the Fermi Large Area Telescope, which observes high-energy gamma rays from distant sources, could potentially detect these delays.
So if we see these delays, it would be a huge point in favor of the time force hypothesis.
It would be a major discovery.
And this idea of quantum foam.
Exactly. And it would also revolutionize our understanding of the very fabric of reality.
It's crazy.
Imagine a world where space and time are not the smooth, continuous backdrop we thought they were.
Yeah.
But a constantly fluctuating dynamic entity.
This is blowing my mind. We're talking about potentially rewriting the textbooks.
I know, right?
On gravity, black holes, and the nature of space-time itself. It's incredible to think that this one hypothesis could have such far-reaching consequences.
It's a game changer for sure.
But I have to ask, is there anything the time force hypothesis can't explain?
Well, it seems like it has an answer for everything. Well, it's still a very young theory.
Right.
And there's much more work to be done to fully flesh it out and test its predictions.
Right.
But even if it doesn't end up being the ultimate theory of everything, it's already pushing the boundaries of our understanding and opening up new avenues of exploration.
That's what I love about science. It's not about finding all the answers.
Right.
It's about asking the right questions and constantly pushing the limits of our knowledge.
Exactly.
And the time force hypothesis is definitely asking some big questions.
It certainly is. And who knows, maybe one of our listeners will be inspired to tackle these questions.
Well, I like that.
And make the next groundbreaking discovery in this exciting field.
I love that idea. And speaking of inspiring ideas, the time force hypothesis also has some intriguing philosophical implications.
Oh, for sure.
We've talked a lot about the science. But what about the bigger picture? How does this hypothesis change our perspective?
That's a great question.
On our place in the universe.
That's where the time force hypothesis takes us beyond equations. And into the realm of existential questions.
I like it.
It challenges us to see ourselves not as separate from the universe, but as integral parts of this cosmic energy flow.
So we're not just observers, we're participants in this grand cosmic dance.
Exactly.
Everything we do, every thought we have, every interaction, it's all part of this energy exchange.
Precisely. And it suggests this profound interconnectedness between everything in the universe. We're not isolated beings, but rather expressions of this fundamental energy that permeates all of reality.
It's almost like the universe is one giant organism, and we're all cells within it.
I like that.
Each playing a role in the overall functioning of the whole.
A beautiful thought.
That's a beautiful and humbling thought.
It is.
But it also raises questions about free will, right?
Yes.
If everything is ultimately driven by this energy flow seeking equilibrium, does that mean our choices are predetermined? Are we just along for the ride?
That's a question philosophers have been grappling with for centuries. The time force hypothesis doesn't necessarily provide a definitive answer. But it offers a new perspective.
What's that?
It suggests that perhaps free will isn't about making choices independent of the universe's laws, but rather about how we navigate the flow of energy within those laws.
So it's not about defying the current, but about learning to surf the waves of energy that shape our reality.
That's a great way to put it. And it suggests that our actions, even the seemingly insignificant ones, can have ripple effects
Okay.
throughout this interconnected web of energy.
It makes you think twice about the choices you make,
Yeah.
knowing that they might have consequences far beyond your immediate sphere of influence.
That's a powerful thought.
It's a call to be more mindful,
Yes,
more aware of our impact on the universe around us.
I agree.
This hypothesis is really pushing me to think about things in a whole new way.
It's definitely thought-provoking.
But let's be honest, as fascinating as it is,
Yeah,
it's still a very young theory.
it is.
There are bound to be some skeptics out there.
Oh, absolutely.
What are some of the biggest challenges the time force hypothesis faces?
You're right. Any new scientific theory,
Right.
especially one as radical as this,
Yeah.
will face scrutiny and skepticism.
Mm-hmm.
That's the nature of science. It's a process of constant questioning,
Yeah.
testing, and refining our understanding.
Right.
One of the main challenges for the time force hypothesis
Yeah.
is that it requires a significant shift in our current understanding
Okay.
of fundamental concepts like space, time, and gravity.
Right. We're basically throwing out some of the cornerstones of modern physics
Yes.
and replacing them with this idea of an all-encompassing energy field.
Right.
I can see how some physicists might be hesitant to embrace such a radical departure
Yeah.
from what they've been working with for so long.
There's a natural resistance to change,
Right.
especially when it comes to well-established scientific paradigms.
Right.
And the time force hypothesis is definitely challenging some deeply ingrained assumptions
Yeah.
about how the universe works.
Plus, it makes some pretty bold predictions, right?
It is.
Like the existence of this quantum firewall at the center of black holes.
Yeah.
And the idea that space-time is this fluctuating quantum foam.
Right. Big ideas.
What if those predictions don't pan out experimentally?
That's always a possibility.
Yeah.
Science is about testing hypotheses
Yeah.
and refining our understanding based on the evidence.
Mm-hmm.
If experiments contradict the predictions of the time force hypothesis,
Yeah.
then it will need to be revised or perhaps even abandoned.
But even if that happens,
Yeah,
wouldn't the exploration itself be valuable?
absolutely.
It seems like this hypothesis is already pushing the boundaries of theoretical physics
For sure.
and inspiring new ways of thinking about the universe.
It's a catalyst for new ideas.
Exactly. Even if the time force hypothesis doesn't turn out to be the ultimate theory of everything, the process of investigating it
Right.
will undoubtedly lead to new insights and discoveries.
Science is as much about the journey
Yeah.
as it is about the destination.
And who knows, maybe some aspects of the hypothesis will be incorporated into future theories, even if the whole thing doesn't hold up.
It's all part of the process.
It's like we're explorers charting unknown territory.
That's a good way to put it.
We may not always find what we're looking for,
Sure.
but the exploration itself expands our understanding of the world.
I agree.
And sometimes
Yeah,
the most groundbreaking discoveries come from unexpected places.
they often do.
Who knows what new mysteries and wonders will uncover as we continue to investigate the time force hypothesis
Yeah.
and other bold ideas that challenge our current understanding of the universe.
It's an exciting time for physics.
Well said. It seems like the time force hypothesis, regardless of whether it's ultimately proven right or wrong, is a reminder that our understanding of the universe is constantly evolving.
It's a journey, not a destination.
There's always more to learn, more to explore,
Absolutely.
more to discover.
I couldn't agree more.
Welcome back to the deep dive. We've been exploring the ins and outs of the time force hypothesis,
Such a fascinating
a
concept.
potential theory of everything that's, already shaken up our understanding of gravity, black holes,
And even the fabric of space-time.
and even the very fabric of space and time.
That's pretty wild.
But as mind-blowing as the science is,
Yeah.
it's the philosophical implications that really get me thinking,
It's a big one.
If this hypothesis is true,
Yeah.
what does it say about our place in the universe? What does it mean to be human in a cosmos governed by this constant dance of energy-seeking equilibrium?
That's where the time force hypothesis really takes us beyond equations
Right.
and into the realm of existential questions.
Right.
It challenges us to see ourselves not as separate from the universe,
Right.
but as integral parts of this cosmic energy flow.
So we're not just observers.
No.
We're participants in this grand cosmic dance.
Precisely. And it suggests a profound interconnectedness between everything in the universe.
So everything we do, every thought we have, every interaction,
Yeah.
it's all part of this energy exchange.
Precisely. We're not isolated beings,
Yeah.
but rather expressions of this fundamental energy that permeates all of reality.
It's almost like the universe is one giant organism,
Yeah.
and we're all cells within it,
I like that analogy.
each playing a role in the overall functioning of the whole.
It's a beautiful thought.
That's a beautiful and humbling thought.
Yes.
But it also raises questions about free will, doesn't it?
Ah, yes, the age-old question.
If everything is ultimately driven by this energy flow seeking equilibrium, does that mean our choices are predetermined? Or are we just along for the ride?
That's a question philosophers have been grappling with for centuries.
Right.
The time force hypothesis doesn't necessarily provide a definitive answer,
Oh, okay.
but it offers a new perspective.
Okay, what's that?
It suggests that perhaps free will isn't about making choices independent of the universe's laws, but rather about how we navigate the flow of energy within those laws.
So it's not about defying the current,
Right.
but about learning to surf the waves of energy that shape our reality.
That's a great way to put it. And it suggests that our actions, even the seemingly insignificant ones, can have ripple effects throughout this interconnected web of energy.
It makes you think twice about the choices you make, knowing that they might have consequences far beyond your immediate sphere of influence.
That's a powerful thought.
It's a call to be more mindful, more aware of our impact on the universe around us.
Absolutely, I agree.
This hypothesis is really pushing me to think about things in a whole new way. But let's be honest.
Yeah.
As fascinating as it is, it's still a very young theory.
It is.
There are bound to be some skeptics out there.
Oh, absolutely.
What are some of the biggest challenges the time force hypothesis faces?
You're right. Any new scientific theory, especially one as radical as this, is going to face scrutiny.
Right.
And skepticism, that's the nature of science.
Right.
It's a process of constant questioning, testing, and refining our understanding.
And one of the main challenges for the time force hypothesis is that it requires a significant shift in our current understanding of fundamental concepts like space, time, and gravity.
It's a big ask.
We're basically throwing out some of the cornerstones of modern physics and replacing them with this idea of an all-encompassing energy field.
Right.
I can see how some physicists might be hesitant to embrace such a radical departure from what they've been working with for so long.
There's a natural resistance to change.
Right.
Especially when it comes to well-established scientific paradigms.
Right.
And the time force hypothesis is definitely challenging some deeply ingrained assumptions about how the universe works.
Plus, it makes some pretty bold predictions, right?
It does.
Like the existence of this quantum firewall at the center of black holes and the idea that space-time is this fluctuating quantum foam. Right. What if those predictions don't pan out experimentally?
That's always a possibility. Science is about testing hypotheses.
Yeah.
And refining our understanding based on the evidence.
Right.
If experiments contradict the predictions of the time force hypothesis, then it'll need to be revised or perhaps even abandoned.
But even if that happens, wouldn't the exploration itself be valuable?
Absolutely.
Yeah.
Even if the time force hypothesis doesn't turn out to be the ultimate theory of everything, the process of investigating it will undoubtedly lead to new insights and discoveries.
It seems like this hypothesis is already pushing the boundaries of theoretical physics.
For sure.
And inspiring new ways of thinking about the universe.
It's a catalyst for new ideas.
Science is as much about the journey as it is about the destination, right?
Exactly.
And who knows, maybe some aspects of the hypothesis will be incorporated into future theories, even if the whole thing doesn't hold up.
It's all part of the process.
It's like we're explorers charting unknown territory. We may not always find what we're looking for.
That's true.
But the exploration itself expands our understanding of the world.
It does.
And sometimes the most groundbreaking discoveries come from unexpected places.
They often do.
Who knows what new mysteries and wonders we'll uncover as we continue to investigate the time force hypothesis and other bold ideas that challenge our current understanding of the universe.
It's an exciting time to be in physics.
Well said. It seems like the time force hypothesis, regardless of whether it's ultimately proven right or wrong, is a reminder that our understanding of the universe is constantly evolving.
It's always changing.
There's always more to learn, more to explore,
absolutely.
More to discover.
I couldn't agree more.
Well, dear listeners, we've reached the end of our deep dive into the time force hypothesis.
It's been a wild ride.
I hope you enjoyed this mind-bending exploration as much as we have.
It's been a pleasure sharing these ideas with you.
And remember, this is just the beginning of the conversation.
Yeah, keep those brains buzzing.
We encourage you to continue exploring, researching, and debating the merits of the time force hypothesis. Who knows?
Maybe one of you will make the next big discovery.
Maybe one of you will be the one to make the next groundbreaking discovery in this exciting field.
It's out there waiting.
Until next time, keep those brains buzzing and those curiosities ignited. Thanks for joining us on the Deep Dive.